So that's my great pleasure to introduce Arunabha Sen, professor from the Arizona State University, from Arizona, close to Phoenix, yes?
Yeah.
Tempe is close to Phoenix, and close to Great Canyon as well. It's a very nice place, hot place as well, southwest of the United States. So he represents the group working mainly on optical networks, computer networks, but they also do research on social networks of different kinds. And this seminar, these talks will be about these kind of problems, and it will be composed of two parts. Entitled here, I wouldn't read it, and we are really happy to have you here. And what is maybe also important, Professor Sen will stay here by mid of May, so for next 2 months. So if you are interested in any kind of collaboration, and you have, I don't know, questions, you would like to talk separately in the small group of people, so you are welcome as well. Yeah?
So, thank you so much. It's a great pleasure to be here. I'm working as a part of this engine project, and first I met Prof, so I thought I'll probably be working primarily on the optical network type of things, but later on I found out there are a lot of people here involved in the social networks area also. I already made 2 presentations earlier on, but I think the audience here is somewhat different. So let me just tell a little bit about myself, my university, the city that I come from, and so on. My background is in electronics engineering. My undergraduate degree is in electronics, and my graduate degree is in computer science, so I can talk to people on both sides of the aisle. Okay, so about this university, it's actually the largest university in the United States with over 83,000 students. We have 250 undergraduate majors, 100 graduate programs leading to MS PhD degrees in liberal arts sciences, engineering, journalism, education, business, all kinds of things. One important thing that is missing is the medical school. We don't have any medical school, and probably we are trying to get one, so hopefully it will happen sometime. The engineering school is the largest in the country, over 13,000 students. The computer science and engineering program in which I belong, it probably very well be the largest. I'm not absolutely sure if it is. We have, in the computer science program alone, we have more than 3,000 students. So this is the city of Phoenix, and you can see that it's a pretty nice city. Only bad thing is a little bit hot. Okay, except for summertime, I think other times they're pretty pleasant. So it has mountains, and if you drive a couple of hours, you get to the ocean. These are some campus buildings. This is the oldest building in the campus. It's called Old Main. These are some of the newer buildings. So it's a pretty nice place, and the city of Phoenix is actually the 5th largest city in the country. I think the greater Phoenix area has about 4 million people. So you were asking, it's not a campus town. It's not a campus town. It's a very big city. Okay, so the type of things that we do, we basically say we do network science at Arizona State University, and we call our laboratory for the science of network existence. So we say this is our motto: we live in a network world. Our computers are network, power grids are network, transportation systems are network, water distribution systems are network, biological systems are network. Even we are networked through our social networks. The goal of research group of the lab is study fundamental science behind all these different kinds of networks. Now, our view of network science is basically comprising of many different disciplines. These are some of the application areas I mentioned: computer networks, power grids, water distribution, transportation, social networks, biological networks. I personally have worked on computer network side. I have worked on power grid. I have worked on social networks. I am trying to do something in the water distribution. Yes, but others I haven't. There are my colleagues who are working in the biological side and so on. And some of the tools and techniques that we use here, they come from things like graph theory, game theory, probability theory, machine learning, data mining, chaos theory, statistical mechanics, dynamical systems, and all these different types of disciplines. The difficult part is that learning any one of them is hard enough to learning. Okay, so actually I started a workshop called Network Science for Communication Networks, and it has been going on for last 6 years. The 7th year it will be actually in April with conjunction of IEEE Infocom conference, which is a major communication network conference. And this has been going on for last couple of years. We primarily organized that. We essentially started this workshop 7 years ago. Now, to my pleasant surprise, that I just found out that network science here at this university, and net science is a much larger conference compared to the workshop that I mentioned. The focus of the workshop is only on the communication network science, whereas the focus of this one essentially covers pretty much every type of network that I mentioned before. So that's about, so I was very surprised, pleasantly surprised that a lot of people are interested in the network science side of things also. Okay, so with that, let me get started on the two topics I indicated at the beginning that I'm going to talk about. Now, the context of our research in social networks, as I said, that this is, I work primarily on the communication network side, but I have been working on these social networks after I got involved in this Minerva project, which started in 2009 and it basically finished in 2014. That the first phase, actually we just submitted the second phase with Paolo and all these other people involved there who are so involved this project. This is actually a very large project. It was a very large project, and it had it involved social scientists, political scientists, mathematicians, mass communication people, and so on. The idea is the finding allies for the war of words, mapping the diffusion and influence of counter-radical Muslim discourse. Now, America has been involved in war in Iraq and Afghanistan for the last 10 years or so. Now, at some point of time, there was a realization that unless you understand the local situation, demographics and all, then it's very difficult to win these kinds of warfare. So they put a lot of money to do social science type of research, and this was one of the effort, and we are the first ones to got this. Mark Woodward, he is an ethnographer. He essentially lives in Indonesia. He lives in Indonesia, and he basically interacts with the local people, what they are thinking, how they're supporting this, they are not supporting these kinds of things. The counter-radical, see, most of the time we hear discourse about young Muslim people becoming radicalization and all that type. We don't hear a whole lot about counter-radical Muslim people. So who are the people who are trying to engage in people who are trying to become radicalized, and what can be done about this? So Riva Castriona is a political sciences scientist from Sciences Po in Paris, France. She's a leading authority in this type of activities. She was also part of the team. He's a social science sociologist, and he's a political scientist. So, and then we had my colleague Hassan Dawat, who is a computer scientist. Tom Taylor is a mathematician. This professor is a professor of communication at this university. Now, as I mentioned, who were the counter-radical Muslims? Islamic radicalization, one of the most security concerns presently confirmed in the United States, and this I'm talking about 2009. And more recently, it has become a major problem in Europe also. An effective containment of Islamic radicalism requires the ability to recognize and support counter-radical voices. Current knowledge is limited by overriding focus of extremists and Middle East. This is the RAND Corporation, is a major think tank in America. Now, who are the counter-radicals? So we have to have some sort of definition. So counter-radicals reject violence as a means of political, religious, or social objectives. In Muslim countries, they manifest in many forms. They are not necessarily secular. They reject radical religious practice, support some or all of these type of things. Contextual interpretation of Islamic texts, local modes of religious cultural practice, popular culture, performing arts, religious pluralism, empowerment of women, democracy, and these type of things. These are the people who support these type of activities, as opposed to radicals who probably don't agree on many of these things. Now, the project goal was to map the radical counter-radical Muslim network. So the discourse that is going on between the radical counter-radical in the community. Map counter-radical and radical concepts, voices, and who is saying what, doing what. with whom, how, with what intent, identify competing and synergistic strategies, access the impact, popularity, and spread of voices and content, focus on understudied strategic regions. Now there are basically three parts, probably this part I'm not sure you can see this is too wide. So basically there are three components. One is the ethnography. I mentioned that our lead PI himself is an ethnographer, and the interpretation of messages, symbols, leaders, media. The part the computer science people essentially did was basically the web mining and mapping, aggregation, interaction, phase shift, notice any difference in the opinion in the network, influence. And then the third component was survey, which was basically conducted in going into locations, social political opinions, consumer profiles, demographics, and all of that. And basically one thing fed into another thing, and then we had the validation, verification process also. So methodological integration, survey is one component, ethnography is another component, and survey web mining data help generalize ethnographic cases. Ethnography provides context for survey findings, survey and ethnography, and basically these three loops together to get the final results and so on. The focus of our attention, the region of interest was Europe, West Africa, Southeast Asia. I mentioned that the PI of this proposal, he lives in Indonesia, he knows that region quite well. In Europe we had, actually this is a very large project, something like probably 20 to 30 people or maybe 40 people involved in different parts of the world. The West Africa is countries like Nigeria, Niger, Chad, and all. Southeast Asia was Singapore, Malaysia, Indonesia, and Europe, basically we focused on three different countries. One is United Kingdom, UK, France, and Germany. So these are the three European countries those are focused on, and all three countries has large immigrant population, and there are all kinds of issues in those countries. So now with that respect, actually, and one of the talks that I'm going to focus on is spatio-temporal signal recovery political tweets in Indonesia. So basically the goal was to construct a political heat map of the provinces of Indonesia from the tweets generated in Indonesia. So we basically collected the tweets and tried to identify which province of Indonesia was more active in these kinds of activities compared to some other provinces. That the political heat map is to indicate the extent of radical activity in various provinces of Indonesia. So the final product is going to look something like this, so that you can see that these are different provinces. Darker red indicates that these provinces are quite active, which are not so dark indicates that these activities are not that much in those type of provinces. So this is basically what we wanted to compute. This is going to be the final product, and I'll come back to that and say how we did that. Now the other type of thing that we are interested in, that influence propagation in adversarial setting. Now this I'm talking about 2010-2011 time frame, 2011 time frame. Now those of you who are familiar with this area, that in last few years, maybe last 10 years, influence propagation in social media has become an important area of research. One of the earliest papers written in this area was David Tempe and John Kleinberg at Cornell University, and they basically laid out some of the foundation work in this area. Now, when I was looking into this in 2009-2010 time frame, what I found out that all the work that has been done till that time, most of it is essentially for influence propagation in non-adversarial scenario. Now what I mean by non-adversarial versus adversarial scenario, non-adversarial scenario means that there is one player essentially, and one player comes in and wants to sell the product or ideas, whatever it is, that in an environment where it's completely new. I give examples like, for example, Coke. Well, when Coke came to Eastern Europe after breakup of Soviet Union, so essentially Coke is the player, Coke is selling his product, people are not exposed to Coke. So how basically Coke is going to capture the market. So that is primarily the focus of research in influence propagation. That was, I'm talking about 2009-2010 time frame. Now, the scenario that I was considering is essentially not that type of scenario, because our thoughts were driven primarily by this Minerva work that we are doing, where American troops were engaged in warfare in Afghanistan, Iraq, and all that, and their adversaries. So the American troops are essentially going and telling people that we are the good guys, everybody else is the bad guys, Al-Qaeda is the bad guys, and Al-Qaeda is saying exactly the same thing. Okay, so the Americans are the bad guys, we are the good guys. So the question is that who is essentially winning this? So who are the common people listening to? So who are they believe the Americans are the good guys, or the Al-Qaeda is the good guy? So that's the type of scenario I wanted to study. That's the type of scenario I wanted to study. And I couldn't find a whole lot of study in that type of scenario, adversarial. So most of the time was non-adversarial scenario. Okay, so we worked on that, and we had a paper in 2012, this conference on information and knowledge management, and influence propagation and adversarials, and how to defeat competition with least amount of investment. And what I mean by that is that, let's say there is one player has influenced some key people in the community, and they are spreading their influence, and an adversary comes in. An adversary wants to have a larger market share. If I go back to my Coke analogy, then suppose Coke is going into the new market and Coke is spreading its influence. Now a new player, Pepsi, comes in, and Pepsi is trying to counter Coke. Okay, so what Pepsi wants is that Pepsi's market share should be larger than the Coke's market share, and what Pepsi wants to do is basically try to find out how much incentive it has to give and what is the least amount of incentive it can give, so that eventually when the spreading process stabilizes, the market share of Pepsi is going to be larger than the market share of Coke. So that's the goal. That's basically defeating the competition, and influencing in that type of scenario, some free samples of Coke or free samples of Pepsi and things of that nature. But then Pepsi doesn't want to give free samples to everybody. They probably want to give as few free samples as possible. Now they want to give as few free samples as possible with the objective, in the end, the market share of Pepsi should be higher than the market share of Coke. So that's basically what we try to understand, how this can be done and so on. Okay, so now this I guess many people know this. Individual research of the product is influenced by recommendation of friends and acquaintances. Now influence maximization problem, I mentioned that what I found out around that time is that most of the studies focuses on non-adversarial information propagation. What I did find out is that there have been some studies in what we call adversarial with passive adversary. Now what I mean by passive adversary is the scenario people haven't quite studied in the marketing type of environment, but in the spread of disease, public health environment, in the disease spread type of scenario. Let's say disease is spreading, and what you do is basically maybe inoculate some people, okay, maybe vaccinate some people, so that your goal is to try to stop the spread of the disease. Okay, stop the spread of the disease. It's not, if I say, let's say the people who are sick, I identify them with the red nodes. People who have been vaccinated, maybe blue nodes. The red nodes obviously are trying to spread. Now the blue nodes are not trying to spread. Blue nodes' goal is to try to stop the spread of red nodes. So that's what I mean by passive adversary, as opposed to Coke and Pepsi, where Coke wants to spread, Pepsi wants to spread. So the red nodes are spreading, blue nodes are spreading also. And I found studies on this area, I found studies on this area. Studies in this area seem to be very limited. We could hardly find 3 or 4 papers where we had this. So this is basically a pictorial depiction of that. So here only one player influence propagation in non-adversarial scenario. These red nodes basically have a free field, and essentially red nodes keep spreading. Red nodes keep spreading. This is the scenario where influence the adversarial, passive adversary. The number of blue nodes, you can see that there are 4 here. It continues to be 4. It's not becoming larger and larger, as opposed to the third scenario where the number of red nodes is increasing, number of the blue nodes are also increasing. So that's the type of scenario that we are trying to study. So this is basically another example of that. So this is red nodes are becoming more and more red nodes. Passive adversary is basically trying to stop that. And eventually the active adversary, the number of blue nodes spread, number of red nodes also spread, and that's the type of scenario we want to do. Now this is what we call winning with minimum investment. We want to give as few free samples as possible, but with the goal of having a larger market share than our adversary. The two vendors players are trying to sell their competing product by influencing the nodes of social network. Goal of both the players having a market share that is larger than its competition. First player has already chosen a set of k nodes. Second player is aware of the first player's choice. Objective of the second player is identifying the smallest set of nodes so that the number of nodes influenced by the second player will be larger than the number of nodes influenced by the first player in these time steps. Every time step the yellow nodes are becoming either red or blue. So when after a certain number of time steps, what the goal of the second player is to have larger number of blue nodes compared to red nodes and so on. So we have the graph representing nodes can be in one of the following three states: A, active by adopting the product A, or active by adopting the product B, inactive, and inactive meaning that at some point of time it may become red or blue. So at some point and IA is the set of initial adopters of this product, IB is the set of initial product and the set of initial adopters. Now, how this influence propagates, then we obviously need some sort of influence propagation model. We need some sort of influence propagation model. And as I said that in the earlier studies, most of these things were focused on non-adversarial scenario. And there have been propagation models proposed for this. There are a number of propagation models for non-adversarial scenario. There are a number of propagation models proposed for adversarial scenario. But there are not a whole lot of propagation models proposed for adversarial scenario with active adversary. Now the non-adversarial, I mentioned David Tempe and John Kleinberg started this with a paper in KDD in 2003. And when I was looking for propagation models for adversarial scenario with active adversary, we could find only one paper, and this is Tim Kearns and his students and the International Conference Electronic Commerce, they maximizing influence in a competitive social network. So this is one paper we came across where they are considering exactly the type of scenarios that I was considering, that the two competing forces trying to spread their influence in a competing environment. Only thing is that their objective was somewhat different in the sense that in my scenario I was saying that the Pepsi comes in and Pepsi wants to have a larger market share than Coke with the least amount of investment. Whereas what they are doing is basically Pepsi has a fixed budget, Pepsi can influence only k number of nodes and try to maximize their influence. The maximum influence need not be larger than the market share of the first player. So they are not trying to beat the first player as I'm trying to beat the first player, okay, with the least amount of investment. So they have a fixed budget, they are trying to maximize the influence. I don't have a fixed budget, I want to minimize the budget with the goal of beating the opponent, okay. Now the good thing about their paper was that they had some models. They had some models for the type of scenario that we are considering, that is the influence propagation in active scenario. And actually all these guys were students in John Kleinberg's class in that topic. Okay, so these guys are all, and I think they started doing it as a class project or something. Okay. All right, so we basically did not propose any new influence propagation model. We pretty much used the influence propagation model they used, which was sort of variations of the propagation models that Tempe and Kleinberg proposed in their 2003 paper. There are two propagation models that they considered. One is the linear threshold model and independent cascade model. And what they did, Tim Kearns and his colleagues, they modified some of those models to develop two different models, what they call distance-based model and wave propagation model. I'll just describe that in a minute. When the node becomes, it has a single chance of activating each currently inactive neighbor V. An active node may influence its inactive neighbor with the probability V. gives a set of active edges, that is successful attempts. Once a node adopts a product, it will not change it. So this is one thing, that if a yellow node or white node becomes red or blue, it stays that way. It doesn't go back to yellow, or so that is not allowed, but it seems that it can be incorporated. There are people who have done that, and it seems it can be incorporated, that the changing colors is allowed. But in the study that we have done, we didn't allow that. So we had only, once it becomes red or blue, it stays that way. Inactive node may be influenced by several active neighbors in different states. So these are the two models, they are models. And the distance-based model, what happens, the probability of some node U adopting the product B is given by this relationship, and what this one is saying is that the DUEA is the shortest path distance from node U to the initial adopters or along the active edges. So basically, in the graph, we identify some active edges and find the shortest distance from the node U to one of those initial adopters. And this is the set of nodes at distance, shortest distance from U. And same thing for, this is the number of nodes which has adopted this product A, and this is the set of nodes which has adopted the product B. And then from that we compute the probability of some node U accepting the product B with this type of relationship, And so if, let's say, these two blue nodes are the initial adopters here, and this is the red node is the initial adopter at time t equal to 0. So the shortest distance for shortest distance, if this node is trying to, what is the probability of this node turning into red or blue? So the shortest distance to its initial adopter is 1, and both of these are 1, and there are two nodes within distance 1 which is blue, and there are one node with distance 1 which is red. So the probability of this node becoming red is 1/3, and the probability of this node becoming blue is 2/3. So that's how this distance based model, the propagation model, that's how the probability of propagation is computed. So similarly, using that sort of formula, all these probability values are computed. And just see, now in case of weight-based model, the probability is computed in a different way, and it's sort of more like the independent cascade model. So SU is the set of neighbors that are closer to I, that's, let's say, at some time state D, and before that D minus 1 neighbors, the distance have been already computed. Instead, every node that has a distance D from some node I chooses one of its neighbor distance D minus 1 from I independently at random and adopt the same technology as its neighbor. So this computation is slightly different from the previous one, and these probability values also turn out to be something different. So the computation goals are slightly, so here it turns out to be 2/3 and 1/3, and as you can see that the previous one we had 1/3 and 2/3 and so on.
How do we get the value for the lowest node, the yellow one? Why does it have 1/3 and 2/3?
This one here?
Yeah.
Okay, this one here, okay. So see that in this distance-based model, what it does, it pays attention only to the initial adopters. Initial adopters here, it's two blue initial adopters and one red initial adopter. Okay, for this one, so basically there are two blue nodes in the initial adopting set. Okay, and there is only in the distance. So what is the shortest distance from this node to the initial adopting set? Initial adopting set is 3 here, right? And what is the shortest distance from this node to a red node, which is 2? Okay, and what is the shortest distance from this node to a blue node, which is also 2? So there are two blue nodes within the shortest distance of this guy, and there is one red node within the shortest distance of this guy. So those are the only ones, they play a role in determining what this probability value should be. That's how this distance-based model is defined. So they pay attention only to the initial adopters.
But if this intermediate node is infected by blue, so it also...
See, the intermediate nodes don't play any role in the distance-based model. It does play in the wave propagation model, the next model. Okay, next model essentially what it does, it pays attention only to the ones that has transformed in just the previous iteration. Okay, so this one just is the oldest time, and the other one is the nearest time, d minus 1 time. And so these values in the previous case, this turned out to be carrier union IB. In the distance-based model, they pay attention only to what is happening here, how far is the nearest distance and so on and so forth.
Oh, we understand, but is it realistic from a social point of view? Why?
Well, see that now the other model, what it does, see that at next time step, this may become infected, this may become infected, this may become infected. This is how it propagates, right? So the second model essentially pays attention only to these guys only. The second model pays attention to only to these guys. The first model pays attention to only to these guys. Now that's the model, okay? That's the model. Alright? Okay, so with those two propagation models, our objective of our winning with minimum investment problem, we want the expected number of nodes to adopt B should be larger than the expected number of nodes to adopt A. So given the set of nodes which has already been influenced by product A, the propagation model and the number of time steps, objective is to minimize the set of initial adopters of B such that the expected value, what is written here, the expected number of nodes, which is this value. Actually this is not a division, this is not being divided by this, this is basically same as this. It's basically algorithm appear that it's being divided. So this quantity should be greater than that quantity, which is denoted by sigma B. Sigma B IA IBT, which is the expected number of nodes to adopt B, should be larger than the expected number of nodes adopted by A. Okay, so next thing we look at what is the computational complexity of this problem. Computational complexity turns out that this is an integer, and with these we basically have some additional nodes here, and then we could basically show that if there is a collection Q that covers S is the original set of elements of the set cover problem, and then IB includes corresponding, and IA, we basically take this node to be the initial adopter of product A. If that's the case, and if there is a set cover, then we can basically say that with the subset less than equal to K, with the initial adopter in a set less than equal to K, B will be able to beat A, and if there is no such set cover, it will not be able to beat K. So it basically transforms to one to another. So we could show that this is an NP-complete problem. Now, then we look for an approximation algorithm for, so GWMI is supposed to read greedy winning with minimum influence. Greedy winning with minimum influence. This is a fairly simple greedy algorithm. So we start with empty set for IB, the initial adopters for B, and as long as the expected number of nodes for B is less than equal to expected number of nodes for A, we keep on adding a node to the set B till this quantity becomes greater than this quantity. And the way to choose that node, once we are considering every node is a candidate node, and then we basically say, okay, if I include this one, how much benefit do I get? And whichever has the largest benefit, we include that node. Whichever has the largest benefit, we include that node. Now that set not necessarily going to be, that set may not be the optimal one, that may not be the fewest number of nodes which could beat this set, but we could show that this is not going to be any worse than a log n factor. It's not going to be a log n factor, W is a log n approximation ratio. Well, basically what we could show that when you bring in one node, then it guarantees a certain amount of increase. And if you have that type of increase, at most you have to, and when I say every iteration we are adding one node. So the number of iterations that you have to go through before you can beat the other guy is bounded by this factor. So the number of iterations that you have to do is not going to be more than the log n times the optimal number of iterations that will be needed for that. So now these things, if you want to get into the details of this, these are in that paper I mentioned. I have copies. If you want, I can give it to you. But we could prove that this approximation ratio is log n factor approximation ratio. So we could do that. Now that's the upper bound of this algorithm. So this algorithm is not going to be any worse than this log n factor of the optimal solution. Log n factor of the optimal solution. Now just as we could establish an upper bound, we could also establish a lower bound for the algorithm. The lower bound for the algorithm, lower bound not for the problem, but for the algorithm. What it essentially means is that there are problem instances for which this algorithm will end up requiring log n times the optimal solution. Okay, so again, basically there's a construction that we have a sum graph. Okay, so we basically construct the graph, and let's say this is the initial adapter for product A, and if this type of construction, we could basically establish that in the wave propagation model, if our greedy algorithm is applied, whereas the greedy algorithm is going to end up requiring log n number of nodes, whereas that optimal solution could be just one node. So algorithm, so that basically what it says that our analysis is pretty tight. So our analysis doesn't say anything much about the quality of our solution, whether something better algorithm with better bound than log n could have been found or not. We are not making any comment on that. All we are saying is that our analysis, this algorithm might end up requiring log n. It's not going to take less than log n, and it might end up requiring log n. So that's pretty much what this one is saying. Okay. Now then we did some experiments. So the collaboration data set, scientists posting. So this was from this paper, the structure of scientific collaboration networks in National Academy of Sciences, that came on 2001. So co-authorship graphs representative of typical social networks, and many studies have been done on this type of networks. This one has about 8,000 nodes and 16,000 edges. The connected 5,000 nodes and so on. And the diameter is 19. Experimental setting, propagation model, wave propagation model with uniform. The probability value is taken to be 1. Algorithms that we used to identify the initial set was the degree centrality heuristic. So basically saying that the node with the high degree is important. So that's how the importance of the node is measured. Another way of measuring importance is the closeness, that is the average distance between a certain node to every other node in the graph. So that's called the closeness centrality. And a greedy algorithm, influence maximization, that every iteration, now this is the algorithm that was used in Tempe-Kleinberg paper, which was essentially developed for non-adversarial scenarios. So these are 3 algorithms we use for identify the initial set. Algorithms used to identify IB, again we tried this degree centrality and greedy algorithm that every iteration node increases, node is selected. Let me just, so some of this didn't come out. Okay, so this results basically what you can see that this is the number of initial adopters of A, so 20 and so on and so forth. And these are the different algorithms that are used to choose the set IB, that the initial adopters. And so what this degree closeness means that the first player, that is player A, is using degree centrality to choose these nodes, and second player uses closeness, degree, this second player influence maximization, and this greedy winning with minimum, so these algorithms. Now what this one is essentially showing, is that, okay, so when the value of k is equal to 20, initial adapter A has influence only 20 nodes. In order to number of initial adapters of B, if I using this closeness, I might need maybe 180 nodes to beat, or in this case about 40 nodes to beat the first player. And you can see that the closeness performs the worst. Closeness, so here is this value being 80, what it means that the first player adopts 80 nodes, influences 80 nodes. If the second player uses closeness centrality, it might require 180 nodes to beat the first player. Now, among all this,
excuse me, closeness means that you select the nodes with the highest closeness.
Yes. So let's say this 20 here, the 20 node which has the highest closeness value. Okay, highest closeness value. So the first player uses this one, and the second player also uses, the first player is always using degree centrality. Second player uses closeness. And the second player uses closeness. If that's how the nodes are selected, then it might end up requiring 40 in this case and 180 in this case, where the first player is. So it requires a lot of resources to beat the first player. So it's not that efficient. Whereas as opposed to, as we go to our algorithm, that is the greedy winning with minimum utilization. So this performs the best essentially. So if the first player is taking some value 80 or so, among all these four algorithms, our algorithm performs the best actually. Our performance the best, and it also beats this algorithm, which is the second player influence maximization. This was due to Tim Kearns, who considered the adversarial scenario, but their goal was not to beat the second player. Their goal was to maximize the influence of the first player. So their objective was somewhat different.
So did you try to find the optimal solution, the least set? Because you try to find something, either the greedy, either or the closeness, or the greedy, whatever. But there is also the optimal solution. I know it could be hard for this.
Yeah, see that actually finding the optimal is hard. Actually finding this not optimal is very hard. Okay, finding this non-optimal is very hard. The reason why I'm saying is that, see that we are doing expected values. We are talking about expected values. So basically you need to do with how many instances that you have to work with, so that you have the probability value and doing this, how many graphs that you are working with. For each one of these runs, we have to do 10,000 experiments. This is for non-optimal solutions.
Yeah, I know.
Okay, so this computation of the expected value, is a very difficult, and computing the exact expected value is almost impossible. So people essentially do sort of sampling. Which we also did that. And so basically we took 10,000 samples. 10,000 said that.
But for smaller graphs, it's possible.
Well, smaller graphs it will be possible. But then our graph, I probably would not say it's a very large graph. I say it's about 8,000 or so, probably mid-size. There are other people who are doing much larger graphs also. But these type of things, finding optimal is, unless you have a very small graph, almost it will be impossible to do that. Okay, so definitely not something like 8,000 node graph or things like that. Okay. All right, so that's that. And then we had, how are you doing with respect to time? How much time do I have?
An hour.
An hour. So how much?
By three.
Okay, so about 30 minutes, or how much do you have about? 15 minutes. Okay. 15. Okay.
15.
15. Right? 50. Okay. 50. So then I don't have to hurry. Okay. All right. So I'll just think whether I should speed up or.
But if you wouldn't manage, so we can continue this. I don't know.
No. I think 50 minutes is enough. I'm pretty sure I'll finish up in 50 minutes. I'm pretty sure I'll finish up 50 minutes. So this was basically the performance of this algorithm which we proposed compared to some other algorithm for choosing the influential nodes. And what this one is showing is that our algorithm performs better than most of the other algorithms. And that's not really all that surprising in the sense that closeness was not designed to say that, okay, I have to beat the other guy, so that was not the objective. Okay, that was not the objective. None of these, even this one probably comes closest to this one, but this one also is, its objective is not same as beating the other guy with the least amount of investment, but to maximize the second player's influence, to maximize second player's influence, maximize second player's influence. So again, it's not surprising that our algorithm, which was designed specifically for this, was able to beat all these other algorithms. Now, one other thing that we would like to see is that although these 3 other algorithms, actually ours with 4, it basically, at the end of all certain number of steps, in this case 10 propagation steps, certain number of nodes turn out to be red, certain number of nodes turn out to be blue, and so on. Now, if I'm trying to beat the other guy, not only I want to beat the other guy, I probably would like to beat the other guy with as large a margin as possible. Okay. Now that margin, so winning a football game, so whether I win by 1 goal or 10 goals probably makes a whole lot of difference, right? Okay. So now the difference will be larger. Difference will be larger if one, that the number of red nodes is small or the number of blue nodes is large. So that's how this difference will be measured. And you can see that here what is happening here in this one basically showing that the number of red nodes or the coverage of A at the end of these 10 steps. So what is happening that this is the second player influence maximization algorithm. Second player influence, obviously it is doing better than the other ones. And this is our algorithm. Our algorithm is able to, okay, so this is our algorithm is doing less. It's covering even so this second player is trying to maximize the influence of the second number. It is maximizing the number of blue nodes. What is happening to the number of red nodes? Number of red nodes is this one. In our number of red nodes is this one. So if our goal is to have as few red nodes as possible, even in this case our algorithm is doing better. So the number of red nodes in this case will be this much, whereas our algorithm will perform this much. So this being, in this case, having smaller number is good. In this one, the coverage of B, what is happening to the second player, number of blue nodes should be higher. Now in this case, our algorithm is performing worse than the algorithm designed to maximize. And then again, it's not surprising because this algorithm is designed to maximize the influence of the second player. And it is maximize the influence of the second player. It is maximizing the second player. But again, you can see that it's not that much. It's not that much that the influence maximization algorithm is doing more than this one. Now, one other thing is that, okay, it is doing more, but then with how many nodes? See that it is after how many initial adapters, and coverage of per initial adapter. See that when we see that this one is having more blue nodes than this one, what we are not paying attention to, what is the size of the initial set? What was the size of the initial set? And size of the initial set here was larger than the size of the initial set here. See that this algorithm was not trying to minimize the number of nodes to beat the other guy. So in order to beat the other guy, it required more nodes than we needed. So the number of initial adapters for these guys was less than the number of initial adapters needed for this guy. So if we do some sort of coverage of B per initial adapter, it turns out to be very, very close in all these cases.
Excuse me, what is the objective? I mean, you're trying to find an algorithm that gives you the, in 10 steps, the biggest difference between the blue nodes and the red nodes? So the bigger the difference, the better the algorithm?
No. So the goal is to, so I was talking about these competing players, right? Competing players. So the first player has come in, let's say influence some number of nodes, let's say 10 nodes. And as time passes, more and more nodes are turning into red. Okay? At some point of time, it is going to stabilize. Okay, so at some point of time, if there are only finite number of nodes, it cannot continue forever, right? It cannot continue forever. Now, when the blue node comes in, blue is also spreading, right? Objective of the second player is to have larger number of blue nodes when the stabilization takes place, with the least amount of nodes inserted at the beginning. That is the goal. Try to minimize the original investment. Minimize the original investment, subject to the constraint, eventually the number of blue nodes will be larger than the number of red nodes. That's the objective.
What is the difference between these four algorithms?
So these are basically, okay, so
Strategy of
So
selection.
this is basically what we are saying is that our algorithm is doing better than all these other algorithms. So we specifically compare with this one. See that these two consider this adversarial scenario. These two algorithms essentially convey our goal is different from this other one's goal. The other one's goal is the second player's influence should be maximized. Second player goal is not to beat the first player, which is our goal. So the goal of the second player are two different goals in two different scenarios. In one scenario, this purple one, what it is trying to do is trying to maximize the number of blue nodes. It will be quite happy if the number of blue nodes is much less than the number of red nodes, as long as it is maximizing it. That's not our objective. Our objective is to make sure that the number of blue nodes will be going to be larger than the number of red nodes. So we are considering competing scenarios, but the objectives are somewhat different.
Okay, but the network dynamics, I mean, not the network, but the opinion or product selection dynamics, is it the same for all four algorithms or not? Or you max? Because I don't really get what do these four algorithms differ in?
What do they differ in? Well, see how they are selecting these nodes. So basically, if my goal is to...
So essentially you have four different models.
Well, no, not four different models. It's the same model, four different algorithms. So these are different algorithms for selecting the nodes for the second player. The second player has to select some nodes to beat the first guy, right? So I've said the objective of our problem for the second player to identify some nodes, turn them into blue, so that when this propagation process ends, total number of blue nodes should be larger than the total number of red nodes.
But what is the inflection process?
Those are the two models that's a distance-based model and the wave propagation model. That is how the system dynamics works that way.
Yes, this is related with the game of Go, or for which kind of, because this is strategy.
Well, see that what I'm describing is completely algorithmic point of view. These type of things can be set up in a game theoretic point of view also. So, but then the study could be something different in the sense that there is a Nash equilibrium or not, and so on and so forth. That's basically what game theory analysis essentially studying. That's not what we are studying. What we are studying is what do I need to do so that I can beat the other guy. That's pretty much what we are trying to do. And see that all these four different algorithms can be used by the second player to select these nodes. Okay, all these four algorithms, all this one is saying is that, for example, if the first player has chosen 60 nodes and this influence propagates, maybe in the end there are maybe 6,000 red nodes and so on. So if I'm trying to beat the first player using this algorithm for choice of the nodes of the first player, I might end up needing 120 nodes. 120 nodes I need to turn into blue nodes so that eventually the total number of blue nodes will be more than 6,000.
So the player selects which nodes will be the initial node.
Exactly.
And this is the end of the strategy? Or
Yes.
This is the end. And then the model carries on.
Well, the model carries on according to the model. All we are trying to say.
So only the algorithm, what you call an algorithm, is just the selection of the initial nodes.
Exactly. Selection of initial nodes.
Okay.
This is all about selection of initial
Okay.
nodes.
But what about the competitor? What about the strategy?
Okay.
Which nodes are infected by your competitor? Does it
Competitor,
matter?
okay, competitor has basically follows some strategy. Okay, so for example, here we have taken the competitor strategy. Competitors are using this strategy. Basically, competitor started with say 10 nodes, right? Competitor had to decide which 10 nodes to select.
Yes, I know, but
Ah.
so you have influence on your company, but your competitor
Uh-huh.
has already a certain part of the market.
Yes.
So the question is, which part of the market?
Well-
Does it matter or not?
Well, what we are considering is that what the competitor selected at time t equal to 0. Which 10 nodes, I have the knowledge that which 10 nodes my competitor selected at time t equal to 0. Now, once that is selected, the rest of it, basically the dynamics follows. The dynamics is according to this model or that model, whatever model is being used. So, important thing is to know which 10 nodes. Which 10 nodes the competitor selected. And obviously the competitor had competitor's algorithm to select those 10 nodes.
Yes.
Okay, so here we are just saying, okay, so maybe they have selected this algorithm to select that. It doesn't really matter whether they use this algorithm or some other algorithm.
Random.
Okay, so yeah, so random. So all I know is that these guys selected 10 nodes. How he selected that 10 nodes, I'm not, see that in our experiments we use, we have
the
used
question
some.
is, does it influence the results? Which nodes they have selected?
Well, we have tried several different algorithms for the first layer instead of degree. Okay, instead of degree, we basically tried out all this closeness centrality, degree centrality, and all of that, and all of the.
Not
see that-
random?
Now the thing is that our algorithm is the goal of our algorithm is to beat the other guy.
Yes, I know.
Okay, only that it might affect me is my initial cost. If the first player makes a smarter move, in order to beat me, for me to beat the other guy, my cost might go up. Okay, so this one is essentially the scenario where the first player is oblivious of the second player. How the first player chooses this. We have also considered the scenario, first player is aware of the second player. First player knows that the second player is going to come and try to beat me. What can I do to make sure that the second player will not be able to beat me? One case. Now, or it could very well be that, well, if this person is willing to not beat me in the sense that, well, if you have the unlimited budget for the second player, the player can go on. But if the second player has a limited budget, if I do something, I can make sure within that budget you will not be able to beat me.
Yes.
Okay.
Great, yeah.
So those are various different types of scenarios that we have considered. This one is the first player is oblivious of the second player. That the second player is going to come in and try to beat me and so on. Okay. Alright, so now, did I answer your question? Okay.
So those are initial conditions actually.
Yeah, so basically initial condition. All we are looking for the initial conditions. Yes. Okay, so and this one, see that not only we want to beat the guy, we make sure we will beat the other guy, and we want to beat the other guy with as large a difference as possible, and the difference will be large if coverage of the first player is small and coverage of the second player is large. So here basically what I was showing is that here if I use our algorithm, coverage of the first player is this much, coverage of if I use the other algorithm it's higher. So this is better than that one.
And excuse me, what is the unit of measurement? What is the coverage? Is this 100 or 350? What does it mean?
This is the number of nodes. Number of nodes.
And the whole network size doesn't matter on this? The whole network size?
Yeah, see that here, this is basically, I'm not sure whether this was on that 8,000, it could be, actually we tried for several different ones, smaller one, bigger one. This one, I'm not sure whether it was on that 8,000 node thing. See that, and this is stops only after 10 propagation steps. Okay, so now I said that the stabilization process, if it's 8,000 node graph, and the probability value that we associated with the links was very small, it's 0.1. So the number of active edges, so the graph is essentially a very sparse graph. So it was a very sparse graph, so in order for this entire network to turn into red or blue, the number of steps would have been a lot larger than just this step. Okay, so alright, so and what this one is coverage of B. Okay, so coverage of in this case, so what I was showing in this one, coverage of A we would like to have small, which is the case. Here coverage of B would like to have high, which is not the case. So essentially our algorithm is performing worse than this one, but then that's not unexpected in the sense that this algorithm is designed to maximize the inference of the second pair. Our algorithm is not. Our algorithm is not designed to, but then even then it became close. But then this one, in order to beat the other guy, we are beating the other guy, they are beating the other guy. Only difference is that in order for us to beat the other guy, we need fewer number of nodes. In order for them to beat the other guy, it requires more number of initial investment. Okay, so although eventually the coverage is becoming higher, that is at a higher cost. They use more nodes. They use more initial. If you use 10 nodes, they maybe use 12 nodes or 20 nodes. So if I just factor that into account, is basically turns out that the total benefit that you get out of one node is very, very close. These two algorithms are very, very comparable. These two algorithms are very, very comparable. So this greedy algorithm that I just talked about is turns out to be pretty good, and we have experimentally it turns out to be good. In the analysis also we could establish that this log n type of bound exists. Okay, and this analysis is pretty good. And the number of initial parameters. So you are asking about this, how the first player is choosing. So first player we also turned out to be different types of algorithms. This is the strategy for the first player. This is the strategy for the second player. Okay. Okay. This is the strategy. The second player is always using this greedy algorithm. Okay. First player is turning out many different types of things. Results are not all that different. Okay. So it seems that it doesn't really matter. Each edge has a probability value. Okay,
so in each run, player A chooses a certain number of nodes,
yes.
and it was using his strategy, then player B uses...
Right, so we have basically, if I think of a deterministic instance, from the probabilistic graph we have a deterministic graph. So we say this notion of what is called an active edge. Active edge when it's there, but there is no probability, we basically got rid of probability. We got rid of probability, so basically you can have a whole set of instances. I was talking about 10,000 instances. Okay, 10,000 instances, and every instance the graph looks different. The graph looks different, and so we did that. These are all average values. Okay, so that's about this part. Okay, so this is what we did, and I can talk about the other part. Okay, so Okay, so I already covered all these things. So this is the second part. I don't know if you are too tired to go into the second part.
So it's not coming time.
Yeah, so how
Yes, so maybe we can take, because there's about half an hour left.
half an hour left?
More or less. So maybe we had better move it to another.
So it's completely up to you. So I can, if you think there is half an hour, I probably can finish up this in half an hour. But if you want to do it another day, that's fine too.
I think that we had better more time for discussion rather than only just to
Sure.
speak and nothing else.
Sure.
Yeah, don't you think? Yeah. So we'll find time.
Sure.
Sometime,
That's fine.
and we'll let you know.
So either way
that,
it's fine.
Either to S3 or somewhere else.
How long are you staying here?
Hmm?
How long are you staying in Brussels?
I'll be here for another 2 months.
Oh, yes.
Mid-May.
Plenty of
Perfect.
Not
Yeah.
a lot.
Okay.
Okay.
Yeah, because we will have questions for sure.
Okay. So you are also doing this kind of thing?
Not really networks, but yeah, we are trying to do. networks, but we are making opinion spreading or also
Okay.
diffusion of innovation and also this marketing with advertisements. So in 2003 we published our first paper, in fact about cola wars. So it's
Okay.
exactly
I see, I
the
see, I see,
example.
I see, I see.
So yeah, so we
But
are.
at that time we used only a square bridge, so it was.
Yeah, because it's old times, so at old
Okay.
time, yeah, complex networks and
I
so
see.
forth.
Yeah, this part I can
Starting
certainly.
from 22 slide, because it's not all computation, no real experiment.
Well, see that we had analytical part where I just
Yes,
showed
it's
all this,
it is
and
analytical.
then last part was all about
May
experiments.
you say something about quality of this model? Because this is model, epidemic model.
Well, influence spreading model, there are, I can think of 10 different models. I can think of 10 different models. Now, at least in the public health community, they have these SIR models and SAR models and all that type of stuff. So I think there has been some effort towards validation of the models. Okay, in this domain, what bothers me most that no effort whatsoever in validating any model. So it seems to me that it's completely an intellectual exercise. Whether it is really applicable anywhere, nobody really knows whether distance-based model works or it doesn't work. I can say it works, you can say it doesn't work, and there is no way I can prove myself right or you can prove yourself right.
Well, I have one question regarding your model of spread of influence. You are stating that if a node becomes infected, it also becomes highly committed to that particular product. And is it realistic, this scenario you're analyzing, like marketing campaigns? Because people can change their mind.
People can change,
after
people
some
certainly
time.
can change, persons certainly can change, and see that when we did this work, I was primarily David Tempe and then Carnes, and then there are a whole lot of papers, not in the health community, but in this marketing community, and we didn't see a whole lot of papers which allows a node to change colors, that it remains blue at some point of time, red at some other point of time, blue at some other point of time, and so on. But that type of analysis has been done by the people in the public health community. This has been done in the disease, people who study disease. This is also done by people who study biological networks. Biological networks, there is one professor at Harvard, Michael Nowak, I don't know if you have heard of him. He's a biology person. Well, he's a computation person, but his domain is in biology. And they do a lot of work on where the nodes are allowed to change color. So it's red at some point of time, blue at some other point of time, red at some other point of time, and so on. They have a different model. And I don't know if they have made efforts to validate their model or not. Now this is one thing that I'm not quite even sure how to validate any one of these models. How can I go and say that, well, this is the right model? Actually, many of our work has been funded by various government agencies, and I basically told some of the program managers that we don't need any new models, we know the right one. Nobody knows which one is the right one. Everybody, they are working with their favorite model.
In English,
Sorry. So the suggestion is to have the next step, the next part of the seminar in Tuesday.
Tuesday at 9.
Next Tuesday, next Tuesday. That should
No,
work.
a week from today more.
And actually, the next one is not that long, so I don't think it's going to take 1 hour. See that I probably have about maybe half an hour, maybe 40 minutes.
But maybe we can also discuss about this, this presentation, because we have to think for a while.
Sure.
For example, for this distance-based model, because it was the question about the intuition, why does it
Yeah.
could be potentially equivalent to the reality. So maybe because it shows that we have some initial nodes and we calculate the shortest distance,
Yes.
and we assume actually in the background that this influence propagates through the shorter distance, and the more nodes are blue or red, the highest influence is of these initial nodes through the shortest path.
Right.
So, but in general, if you look at in practice, so this influence goes through the intermediate nodes, through your neighbors.
Right.
So it not necessarily goes through the single shortest path, but through the whole network.
Right.
So maybe we had better calculate the average distance
Okay.
to all the initial nodes, assuming that it goes through the whole graphs in the propagation process.
Yeah, see that
I don't
I-
understand why only initial adopters should
Well,
infect you,
that's-
because in reality, everybody can infect you. Even
True.
maybe even better if he is not initial
But
adopter.
it assumes that intermediate nodes are influenced through the shortest paths. So
Yeah, there is
the
some sort of-
shortest paths, reflect the process actually.
Yeah, some sort of underlying assumption that, well, it's not that the intermediate node did not get infected, they did get infected, and that's why they're paying attention to the shortest path as opposed to longest path or something.
Yes, and it goes through the shortest path, you know. And the intermediate are infected on the shortest path, and the shortest path reflects the process actually.
So there is some underlying assumption.
Okay.
But it's questionable because it is only on one
Yeah.
shortest
Yeah.
path. So that's it.
Część węzłów jest po prostu nieprzyjęta.
See that most of these models you can find some justification or some rationalization. So I
Yeah,
did
but then you
this
assume
because
that
of
you can
this.
infect everybody, in fact, yes, because what you mentioned, that sometimes some nodes are in fact forbidden because they don't want to pass.
See, one of the things that are used to consider this degree centrality, the node with a high degree is supposed to be important.
Haven't you considered random, just random selection?
We did not do random, but then
Because
some
random
other
sometimes
people.
is
Yeah.
great.
Yeah.
Nobody knows.
Right. So random sometimes does just as good as any of these things. I
Yes,
think.
exactly.
Yes, but in your consideration, you assume that infection depends only on initial condition.
Well, that depends.
But my question is, if you consider a situation that infection may be controlled, maybe some reason that there is infection.
Well, see that now when you say infection is
It is controlled because maybe some finance and many other input that may provocate this infection.
okay. So what I was saying is that let's say this is your entire network. So in this problem, the one that I just described, I said that this part is already infected to be dead. Because now how it happened, I don't really know, but I know that this part is infected.
But you didn't consider the reason.
No, we did not consider the reason. We did not consider the reason. Now, here we are talking about players. Okay, so we are talking about player 2, maybe colored blue, and all
Yes,
that
I
describing
understand
that.
everything, but maybe another reason of infection, another input.
So now this player has this player's reasons why this person chose to this. Obviously, probably use some kind of an algorithm to choose this. Okay. Now, what we considered maybe this guy did this one algorithm, this algorithm, or that algorithm, and all of those things. We don't quite know what this guy did, why he chose this one.
I understand
Okay.
everything. My question was a little bit next step.
That is why this guy chose this one.
Yes.
Well, this guy obviously has reason. I don't know. I don't know that reason.
But the reason may be interesting.
Could be. Could be why this person chose those set of nodes.
Okay, so are there any other questions? If there are not, so we can just...
Okay.